We approach numbers from the left, we approach numbers from the right. Okay, so in this first one, I'm giving you a piecewise function. For anything less than 1, we're following the x squared plus 1. So on a graph, your cutoff is at 1, which is usually where we're going to be most interested in what the limit is, if there is a limit, because that's where you can have it be different coming from either side. So from the left, we've got this quadratic. And then at 1 and to the right, we've got a linear. So because we have this in front of us, as we approach 1 from the right, you can see that that limit is, what's the y value as you approach 1 from the right? Bailey. 4. And as I approach 1 from the left, since I'm looking at the graph, what's that, Joey? 2. And so, is it the same from the right and from the left? No. Therefore, the overall limit does not exist. Okay? Now, if we didn't have a picture, if we just had the function, and we knew we were approaching 1 from the right, which one of these is approaching 1 from the right, the top equation or the bottom equation? 1 from the right means bigger numbers than 1. So which one? The bottom one. So if you wanted to see what this was approaching as x approaches 1, you would plug 1 from the right into this equation. 1 plus 3 is 4. If you're approaching it from the left, even though it's an open circle at the end of this piece, it's an open circle at 1 comma something. So you know as it's coming from the left-hand side, 1 squared plus 1 is 2. So you would plug it into that first one. Okay? And the only thing we haven't talked about yet is what is f of 1? Which one would you plug it into if you wanted to actually find what f of 1 is as opposed to the limit? Eden? Right, the second one, because that's when x equals 1, and you would get 4. Again, you're looking at the graph, so you could just see where the closed circle is, 1, 4. So that makes sense. But these two didn't match, so of course there's no way all three are going to match. But it's kind of interesting because even though like 1, f of 1 has to go into the second equation, if we are approaching 1 from the left, we would plug 1 into the first to see where that open circle is, which is a little bit different. Okay, so this little asterisk thing here says the limit of a function as x approaches a equals L, and so equals some answer, if and only if, and we talked about this yesterday, but we're going to reinforce, if and only if the limit as you approach a from the right on the function equals L, and the limit as you approach a from the left on the function also equals a matching L. So symbolically, and we have to get used to reading symbols, which is why I'm consistently going to say, is the limit the same from the left? Is the limit the same from the right? Okay, yes, so then they have the same limit. This is it symbolically. Here's the limit of your function as you approach some value from the right, being some L value. Here's the limit of the function as you approach a from the left, being the same L value. Therefore, the overall limit as you approach a of the function is L. Okie doke. So, really just get used to the notation because a lot of the multiple choices you'll see are very heavy in notation. You have to understand how to read it. Okay. Use the graph of the piecewise function shown to find each of the following. Go ahead on your own and try to fill in these 8. Okay, Marissa, what'd you put for A? Did anybody put anything different? Okay, Mackenzie, what'd you put for B? Okay, did anybody put anything different? Olivia, what'd you put? -3. Can you go up there and show us how you came up with that? Mackenzie, did you watch that? Oh, gotcha. So when I said, did anybody get anything different for part A, why didn't you speak up? So what? All right, so if we're here's -2. If we're approaching that x value from the right, we're tracing along this line, and the y coordinate there is -3. Part C, Mitch, does not exist. And why'd you say that? Right, because A and B were different, left and right were different, so the overall limit does not exist. Morgan, what'd you get for D? -1. Anybody get anything different for that? Sarah, what'd you put for E? 2. Did anybody get anything different for that? Bailey, part F? 2. Did anybody get anything different from that? Part G, Andrew? Anybody get anything different than that? And H, Connor. F of 0 equals 3. Did anybody get anything different from that? Okay. So on this kind of jump location, limit from the left is different than limit from the right. So they definitely, the overall limit does not exist and anyway, and the function value on top of it is something different. On this one, limit from, because this is where we jump to, limit from the left, limit from the right actually is the same thing. The limit exists, but the function value is different. So what does that tell you about the graph? If you weren't seeing it, when the limit value exists, but is different than the function value. Olivia. Discontinuous, exactly. Discontinuous. And on something where the limit doesn't exist anyway, there's no way it can be continuous. So you don't even have to worry about then comparing it with a function value. Okay? All right, so graph each function. So in a lot of ways, we're going to have to sketch graphs to fully understand things. There's algebraic ways to find a limit, but in a lot of cases, the algebraic ways that we soon learn aren't going to be possible. And so you're going to have no choice but to sketch graphs and unfortunately, they're usually of lesser familiar things. This particular function is what kind of function? Linear, quadratic, what would it be? What type of function? Nope, not a quadratic. Quadratics are like polynomials with the highest degree of x squared. This is not a polynomial because the variable's in the denominator. Nope, exponential would be like some base to an x power. Joey? Rational, okay? Rationals are the ones that typically, the parent graph anyway, looks like this, kind of surrounding asymptotes and so on and so forth, okay? So where is the vertical asymptote? Where is this function undefined? Where will there not be a point? Aiden? 0. So we have a vertical asymptote at 0. And this is going to take some reviewing a little bit because we haven't graphed rationals in a while. And the degree of that asymptote is 2. Who remembers what that does for the image of the graph when the degree of an asymptote is even? Because this one here, the parent graph, is 1 over x. The degree of that asymptote is 1. As soon as you make the degree of that asymptote even, what happens? Yeah. Correct. It mirrors over the asymptote. So if on one side it goes towards positive infinity, then on the other side it will also go towards positive infinity. Or if it goes towards negative infinity on one side, then it will also go towards negative infinity on the other. Exactly. It's kind of like an even function being symmetrical to the y-axis. If your asymptote is even, it's going to mirror itself, so the infinity behavior on either side. Now with this one, if we are on the right-hand side of it, anytime you approach a vertical asymptote, it either goes towards positive infinity or negative infinity. What will this be? Are these going to be positive values just to the right of 0 or negative values just to the right of 0, Andrew? Positive. Because no matter what we square, it's going to be positive. And a 1 over a positive will be a positive. Let's also think about this. Let's just plug in 1. If we were to plug in an x value of 1, where would that point be? 1 what? Bridget? 1, 1. If we were to plug in an x value and get just a little bit closer to the asymptote, like let's plug in a 1/2. If I take 1/2 and square it, Nate, what is it? 1/4. And what is 1 divided by 1/4? 4. So if I have an x coordinate of a 1/2, I have a y coordinate of a 1/4. Let's pretend I get crazy and I get really, really, really close to 0. Coming from the right, and I plug in like a 1/10, right? Is a 1/10 closer than 1/4? Absolutely. What is 1/10 squared, Connor? 1/100th. And what is 1 divided by 1/100th? Yeah, 100. So if I were to plug in 1/100th just to the right of 0, I would get a y coordinate of 100. So you can see just how fast that shoots up towards infinity. Now, what guides end behavior in a rational graph? What guides the end behavior? Is this just going to go down forever? How do we figure out what happens out this direction? Horizontal asymptotes, correct. And the horizontal asymptotes rules are the ones that are small over big, big over small, or same over same, right? What is this? What's the degree of the numerator? Joey? No. X would be, x to the first power would be 1. A constant has a degree of 0 over a degree of 2. So that's small over big. So where's my horizontal asymptote? Small over big is, maybe we need to write these down, means y equals 0. Big over small means no horizontal asymptote. Instead, you have a slant asymptote, so your end behavior goes towards positive infinity or negative infinity. And same over same, where does the horizontal asymptote come from? Anybody remember that? Not the degree. Joey? The coefficients, right. So if it was a 5x squared up top and a 3x squared on the bottom, it would be 5/3. Okay, so the coefficient, and it's the leading coefficient over the leading coefficient. I don't have room to write leading. So this particular case, small over big, has a horizontal asymptote at y equals 0. So as my x's get bigger and bigger and bigger, my graph, my y coordinates should be approaching that asymptote value of 0. And we can play around with this particular function. Some we can, some we can't. We can kind of envision, what happens if I plug in an x of 10 as I head out towards infinity, and 10's not all that far. But if I plug in an x of 10, Trista, what's the value of the function? What's f of 10 going to equal? 1/100, which is pretty small, right? And let's pretend I don't want to plug in 10, I want to plug in 100. What is f of 100? Hundred squared is 10,000, so it's 1/10,000th. Is that closer to 0 or further from 0 than the 1/100th that Trista just said? Gets even closer, right? You're getting an even smaller number. So you can kind of play around with mentally plugging in higher and higher x values and realize, yeah, it's definitely getting smaller and smaller towards 0. And this function will never actually equal 0. It just so happens because the numerator needs to be 0 in order for a fraction to equal 0. This numerator is glued in at 1, so it will never equal 0. And it will also never be negative, right? You know it's not going to go beneath that because you're squaring it. Okay? Then on the other side, we could do something similar. If we plugged in -1, we would still get 1. If we plugged in -1/2, we'd still get 1 divided by 1/4, which is 4. And if we plugged in -1/10, we would still get 100, so it's still shooting up towards positive infinity. And that's that behavior that we mentioned of it mirroring the asymptote. And then if we plug in -10, it's still going to be 1/100th. If we plug in -100 and square that, it'll still be 1/1000th. So it's still getting closer and closer to 0. Overall, we could talk about whether or not that function is even or odd, right? It's an even function. Whether you plug in the positive x value or the negative x value, you're going to get the same original function back. Thank you. And therefore, you see symmetry with the y-axis. So, find the indicated limit. This wants the limit as x approaches -1, which is right there. If we approach -1 from the left, and we approach -1 from the right, they're both going to the same point, correct? And what is that y value? 1. It's kind of a funny spot for them to ask for the limit. A lot of times as we get further into this, they'll actually ask about the limit as x approaches 0, because that's where the break in action is. If there's no break in action, and it's a pretty smooth curve through it, in other words, it's continuous through that value, really you can just plug in -1 and see where that point is. F of -1 is 1. If you know it's continuous, then you can just plug in the value and see what the value is, and you're done. And we'll kind of differentiate between all of that. Okay? Next exercise. Another rational, obviously. Before you start graphing rationals, we should factor and cancel when possible. It wasn't possible in the first one, but it's definitely possible here. And when that happens, our x minus 2's cancel, and this simplifies to x plus 2. So this rational function, what happens when factors cancel? What does that create visually? Well, it will look linear, but when you cancel it, there's another feature on this quote-unquote line. It can't equal 2, so what will be at 2? What'd you say? A whole. Right, exactly. When factors and rationals cancel, you're going to have a whole at x equals 2. And more specifically, that whole location will be 2, comma, and wherever that point would have otherwise been on the line. So if x is 2, the point on the line would be 2 plus 2, which is 4. So your hole is at 2, 4. Other than that hole, the rational function looks identical to the linear function that has a y-intercept of 2 and then a slope of up 1 over 1, up 1 over 1, up 1 over 1. So we'll draw that line, and then wherever 2, 4 is, I'm going to erase it and put a nice, very obvious open hole. And no surprise, that's where they're asking me for the limit. What is the limit as we approach 2? So it's not continuous at 2. We can see that because the function value doesn't exist at 2. But the limit can still exist. As we approach, and here's our vertical line of x equals 2. As we approach that from the left, we're approaching 4. As we approach it from the right, we're approaching 4. So the overall limit as x approaches 2 is 4. Any questions? Okay. Anywhere else, because it's continuous everywhere else, the limit value will equal the function value. It won't be much of a special scenario. All right, a piecewise. Let's try to do this without we talked about it a little bit on the front, without the picture first. The limit as x approaches 0. If we want to figure out what that is, we want to see what the limit is when we approach 0 from the right and when we approach 0 from the left. So, oh boy. Marissa, we'll be back to you. If we approach 0 from the right, which formula are we going to plug into, the top or the bottom? From the right, correct. The bottom. Because from the right of 0 means from values that are bigger than 0. And here's the values bigger than 0. So if we plug 0 into that, what do we get? 5. So the limit as we approach 0 from the right is 5. If we're approaching 0 from the left, Mitch, what do you think the limit is? 4. Because from the left means even though this doesn't actually equal 0, we're still going to plug 0 into this because when you are coming from the left-hand side of it, this is the graph that you're following. So the intention as this approaches 0 is for it to be 0, 4. Correct. So since these do not match, our limit does not exist. Okay, and then I'm just going to, now that we kind of figured that out, because if you can avoid like sketching a graph, it's more efficient not to have to do that. Sometimes you'll have to do it anyway. But like in a case like this piecewise, we can actually wrap our head around it. So now that we just illustrated how to do that without a graph, just to make it all come together and make sense, I am going to graph it. A linear x plus 4 has a y-intercept of 4. And then a slope of up 1 over 1. So it's going to look something like this, but then my domain is restricted. We actually only want to see that line when x is less than 0. So here's where x is 0. We only want to see this line when x is less than it. So I have to erase that part of the line, and I also want to put an open circle, so I'm not actually seeing that line when x is exactly equal to 0. And then anywhere beyond that, it's just a horizontal constant value of 5. So starting right at 0 and any place greater, it's a horizontal line of 5. So you can see the lack of a limit there. The intention from the left is different than the intention from the right. Anywhere else on that function other than at 0, no problem. It exists. It's continuous everywhere else. So the limit will exist everywhere else. Good? Take a minute, try to do this last one on your own first without sketching it. Without sketching it. Bridget, what'd you get? Does not exist. Okay, did you evaluate it coming from the left and from the right? Okay. Nate, what is the limit of this function as x approaches 0 from the left? No, it's going to be a number. If you're approaching 0 from the left, which one of these equations approaches 0 from the left? The top or the bottom? The top. And so if you plug 0 into that, what do you get? 0. So that's the limit as you approach 0 from the left. The limit of the function if you're approaching 0 from the right. Connor, what'd you get? 1. Because from the right is the second equation, and the cosine of 0 is 1. They don't match, they don't exist, okay? Visually, this graph is the graph of the line y equals x, which is just the perfect diagonal. But they only want it when it's less than 0, so I'm going to get rid of this section that's greater than 0, and I'm going to make an open circle right at 0. And then the cosine of x when it's greater than or equal to 0. So at 0, the cosine is 1. And then at 2 pi, it's going to be that again, right? So 2 pi, and unfortunately, I've already scaled my axis counting by 1. So 2 pi is 6.28, right? 1, 2, 3, 4, 5, 6.28-ish. Which means at 3.14, it is at -1. And then at 1.57, it hits a 0. And then again, halfway between these, it hits a 0. And so it looks something like that, roughly speaking. It will oscillate in its future. Okie doke. Any questions? Okay, so your homework is there.